Good day, everyone. We will try to complete or to have this discussion on the DC circuits or the direct current circuits. We are going to mention or to give examples on how series circuits where resistances that are connected in series circuits are dealt with. How do we employ the different principles governing series connected resistances? And likewise, we will give us as well an example on parallel connected resistances. So we will move on to our next slide and see an example of our series connection. Okay, we have here a slide that is showing us series connected resistances, and we kind of arrange the sequencing of the names of the resistances, starting with R1 at the top, R2 and R3, where R1 again is 24 ohms, 50 ohms, and then R3 is 10 ohms. Now, the one that will supply that will provide the power or the current is the battery that is around 8 volts, and this is how the battery is connected. The positive side is pointing up. So now, let's just have a summary of our equations first. What rules or what principles governs again our series connection? So let's have a rundown of this principle. If we will try to look at some notations there, now we will be calling a symbol which we will call as total current. And this total current is the one that we will see, that is starting from the battery. So we know that it starts to get out of the battery from the positive side. And again, now we give it a name and we call it as our I sub t, or I total. So that's again the current that comes out from our battery. Now, as the current is going into our first resistance, maybe it's just appropriate to give it a new name, and we will now call it as I sub 1. I sub 1 again is the current from or the current passing through resistance 1. Now, for the current that passes resistance 2, so as it goes out, current I1 as it goes out of resistance 1, it will now enter resistance 2. And then therefore, as it also comes out of resistance 2, then that next current will now enter resistance 3, and you will see that as it goes out, it will now go back to the battery. Now, if we call I1 as the current that passes resistance 1, we will call I sub 2 or I2, current that passes resistance 2. And then the last current here, we will call it as I sub 3. That's the current that is now entering or is passing through resistance number 3. Now, we realize that for our series connection, we have the following rules. So we realized last time that currents are equal. However, as current and resistance interacts with one another, it will create a voltage. So in each of these resistances, there will be voltage drop or a voltage that results. And these voltages, they are related to the total voltage by summing it up. So let's write down those formulas again. Now, what we have here is a summary of the principles governing our series connections or series connected resistances. Now, since we identify I1, I2, and I3, now we see that it is just simply entering and getting out of a resistance, and again, passes through to the succeeding resistance without ever changing it. So we can probably conclude that the first principle again for series connection is that the currents are all equal to one another. Now again, as the current and the resistance interacts, we see that they will develop a voltage. Now, in terms of the voltage, we see that the three resistances here having individual voltages, when you sum them up, they simply is equal to the total voltage. Now we also kind of summarize the relationship of the resistances with each other when we connect them in series, and they eventually have a total resistance. So let us say now that these are the things that we are trying to find for this circuit. Now let us say that among the things that we will try to find, given this resistances and this voltage, we're trying to find the total resistance first of all. Next, we want to try to find the total current. How much is the current that will eventually the current that that the battery will eventually pass through the circuit. So we will try to find that out. And likewise, how much is the voltage that we will get across resistance 1 and resistance number 10, resistance number 3. So resistance 3 will have 10 ohms, resistance 1 will have 24 ohms. Now, from among the values of the resistances, R2 has the highest resistance. So if resistance and voltage happens to be proportional, then we will see that V2 must be the one with the highest value among our 3 voltages of resistances. Now, R1 and R2 or R3 will have the lesser values of voltages. But again, that's the one that we will try to find. Now, to get V1 or V3, then we need the currents I1 and I3 multiplied by their individual resistances. Now, let's start with our resistance total. So R total would be R1 plus R2, and adding it with R3. Now, I think we add all this, and we have since we only have 3 resistances, then therefore we stop with R sub 3. But if there are more, then you can just simply continue the addition of our resistances. So that will now give us the first value of R1 to be 24 plus 50 plus 10. And it will now give us the next value of our R total. And that will be around 84. So our first value again is 84 ohms. Adding 24 plus 50 plus 10. It now gives us 84 ohms. Then therefore we move on and determine the total current. So if I sub t again is the total current, we will be dividing here the total voltage, which is from the battery. And if you divide that by the total resistance, then therefore that will give us the total current. So again, the total voltage is 8 volts. Divide that by 84 ohms. So you'll have a small value here, and that will now give us 0.095 amperes. So we use 3 digits because I think if we try to round this off, this will with 2 decimal places, we will end up with 0.10. So let's just use 3 decimal places there. So we have there 0.095 amperes. So that's a very small value again, considering that the resistance in the denominator is quite high. Okay, so we have 8 volts divided by 84 amperes. Now, what's the significance of getting the total current? Now, from our first principle here, that will tell us that the currents that are passing in and out of our resistances are all equal to 0.095. So I1 will be this value, I sub 2 as well, and I sub 3. So all 3 or all 3 currents of the resistances are equals to this number. Now, therefore, since we know the currents and we know their individual resistances, then therefore we are ready to solve our V1 and V3. So if we solve for V sub 1, that will be I1 times R1, which gives us Okay, so if we will just remove the unit now, ampere, so we'll just have that decimal number. And if you'll multiply that with R1, which is 24, no? So we are now ready to get the first value of our V1. No? For our V sub 3, that will be equal to I3 times R3. No? And again, I3 is still the same as I1. And however, multiplied by 10 ohms. No? So among these two, I think it's easy for us to find V3, which is 0.95 volts. And we expect that this is the smallest value compared to our V sub 1. So we will multiply the value for V1. Our V sub 1 is now equals to 2.28 volts. Now we notice that there's only V1 and V2 or V3. However, if we are able to find V sub 2, when we determine V sub 2 and add all values V1, V2, and V3, they should all be equal to 8. So the supply voltage being 8 volts. So if we will try to satisfy the rule, the second rule here in our series connected resistances, then the last voltage V2 is simply the sum of these two minus 8 volts. Or you can also get that by multiplying I2 with R2. So more or less, these two are it's around 3 volts ang V1 and V3. So if this is 8 volts, so more or less it's something like near to 5 volts, the value of the voltage in resistance 2. So, but anyway, that's not part of what we are trying to find. So this is now the three values that we look for. So number 1, number 2, and this is our number 3 requirement. We solved for 2 items. So that's our series connection. And again, you have to remember the rule here. In order for you to apply the series connection, you have to know these three rules. So we showed a while ago the circuit that is series connected. Now we will have here parallel connected resistances, but we are going to rename some of these values so that we will have an orderly number. So we will change this to R1, R2, and then R3 above. So let's just change them for a while now. Now we were able to change the values, or we simply rearrange the assignments of R1, R2, and R3, but we use the same numeric value. Now our battery below is providing the circuit with a 12-volt source. So this is now resistances that are connected in parallel. Now if we will have a summary as well of the principles that are connected in parallel, so we will come up with a summarized values there. Now before we go to those summary, let us remember that when the circuit is closed, or when we turn on the circuit, the current will eventually get out of our battery and will now go into the resistances. However, as it goes into the resistances, it will pass through 3 points or 3 resistances. And in that direction, or in that as the total current from the battery enters a junction where the 3 resistances are connected, that current from the battery eventually splits into 3 different directions. So maybe we can call the first direction of the current as I sub 1. Next is I sub 2, and eventually this one is I sub 3. So the current will split in 3 different directions. Let's give them a label. Okay, providing a name. So the current that gets out of the battery, the one that is getting out of the battery and going into the resistances, we call it as total current again, I sub T. The battery voltage is the total voltage V sub T, and the individual currents I1, I2, and I sub 3. Now let's have a summary of our equations or expressions now governing parallel connection. I think we've summarized that last time. No? So let's have it. So the principles, now I think the very first principle that we will see here is that of the voltage. Now we understand no, that if series connections, they all have equal currents here, no, they will have equal voltages. No? So that's a very prominent principle. No? And we only distinguish, or we make a distinction no, of the parallel connection no, with the equality of the voltages of every gadget that we connect in parallel. So that's the very first principle here. Now next will be our current, no, I total. And we understand that if the current, no, as it enters the junction on this side, no, and going into the resistances, that the current simply split. And then therefore, no, the individual currents will simply have a sum, and their total no, should be equal to the supplied current from the battery. So what we mean here is that I total will simply go no, into the different resistances. And again, no, if resistance and current no, somehow have an inverse relationship, then therefore no, the resistance no, that has the highest value, the amount of the current that passes that resistance with the highest value will be the least. No? So from among our list of resistances here, no, 24 is our highest resistance. So therefore, we expect that I sub 2 no, must be the current with the smallest value. So that will be our no, relationship of the current. So the currents again are added together to get the total value. Now let's have the resistances. Now, in terms of our resistances, no, we will get the total resistance, no, not directly, but the reciprocal of the total resistance is actually no, the sum also no, of the reciprocals of the individual resistances that are no, connected in parallel. No? So again, no, we tried this reciprocal equation last time no, in capacitor. So therefore, we have at least no, an idea how to deal with that. No? But again, no, as a summary, here are no, our three principles that governs parallel connection. Now, let's say we are given this circuit and we will try to find no, among the values here. Now, let's determine, again, no, we will find first is maybe no, the total resistance. So how much is that value? Next, number 2, we will try to find again the total current. No? And naturally, no, our next value maybe now we will try to find our V sub 3. No? And last value probably to find is we will try to determine our I sub 2. No? So we have at least no 4 values to find here. No? Now, not like our series connection. No? So we will use or employ a different set of principles here no, to be able to find our values. And I think no, among the values that we can readily get is our voltage. No? So I think no, from 1, 2, and 3, the very first value that we are able to find no, is V sub 3. No? Okay, now I think I2 as well no, can be determined. No? So since we know the voltage and the resistance in resistance 2 no, is there. So let's try and answer number 3 and number 4 no, first. No? So since we could find that value first. No? Okay, beginning or starting with V3. No? So we know V3 since they are the resistors here are attached in parallel. That if we know the supply voltage to be 12 volts, now since R3 now is in parallel to the battery, then V3 now, which is the voltage of resistance 3 or resistor 3 now, is equals to 12 volts as well. So we don't need to calculate that even. No? Now for problem 4 or question 4, no? So if we will solve for I2, then I2, since that's current, no? If we know voltage 2 and we divide it by resistance 2, then we are able to find I2, no? Actually, no, we don't need the total resistance there or the total current, no? But since V2 is 12 volts, and if we divide it with R2, which is 24, no? 24 ohms. So 12 over 24 is half, no? So maybe we can say that there's around 0.5 amperes, no, of current, no, for I sub 2, no? So that's one value, no? So if I2 can be determined, then therefore I3 and I1 can be determined, no? And then therefore we can do the addition of these currents and eventually find, no, the total current I sub t, no? But that's one way of doing it, no? But let's look at another approach, no, by using the total resistance, no? So our goal is to answer question 1 next, no? Let's say we try to find, no, the total resistance, no? And of course, when we get the total resistance, we will use, no, the reciprocal principle, no? Now let's solve it over this side, no? So 1 over R sub t, and that will be equal to some values, no? 1 over 16, no? So our R1 is 16, so we get the reciprocal of 16 added to the reciprocal of 24, which is 1 over 24. And then next, we divide, no, 1 over 10. No? So we get the reciprocals of our values here. No? So let's see this one. No? So again, no, there's a line that divides our fractions there. No? Okay, expressing our value now as a fraction. No? So the reciprocal of the total resistance, also 1 over RT, or total resistance, is 1 over 16 plus 1 over 24 plus 1 over 10. No? And our answer is 49 over 240. So that's 49 over 200. And so our value is 49 over 240. So to get R sub t, we are going to get the reciprocal of that value again. No? So RT. So since that's 1 over RT, no, ang 49 over 240. So we will reverse 240 divided by, no, 49, no, to be able to find the actual, no, total resistance. No? So getting the reciprocal, no, so our value is 4.90 ohms. No? So that is if you divide 240 divide by 49. No? Now again, no, the idea of getting the total resistance, which answers question 1, will now give us the chance to find the total current. No? So the next value, if we will calculate the value of I sub t, okay, so this is another way, aside from adding I1, I2, and I3. So we can divide the total voltage, which is 12 volts, no, by the total resistance. No? So since we know the total resistance, so that will be 12 volts divided by 4.90 ohms. So this one now will also give us the value of our current. Now our answer for the total current now is 2.45 amperes. So again, now we solved I2 here a while ago, which is 0.5 amperes. So the other two, if you subtract from 2.45 this value, this will be the sum of I1 and I3. No? But anyway, you can individually find I1 and I3, since this is merely an expression, or using the principle of the parallel connection where the voltages are equal. No? So you can readily find I1 and I3. No? Now again, if you do that, you can simply get the sum of I1, I2, and I3, and probably you will get an answer very, very close, or if not exactly equal to 2.45. 45. But this is another approach, no, other than finding, no, the individual currents, no. So that's our parallel connection, no. And again, please remember the principles that governs, no, our parallel connection. Now, in our next slide, no, we are provided here, no, or we are seeing here a circuit that is now, no, a combination of series and parallel. Now, why do we call this as a combination of series and parallel? Because obviously, now, if we try to look at this one, no, these two resistances here, no, which are basically called R2 and R3, no, are not in series. So if you examine them carefully, they are actually, no, connected in. They are connected basically in parallel, no. So the way we combine the resistances here, no, will also, no, depend on parallel connection, no. Now try to imagine that we combine that, no, already, and we eventually, no, end up with a single resistance here. After now you combine the two, so you could end up with a single resistance here, no, which we now call as R23, no. R23 because it's the combination of resistance 2 and 3, no. So if you are going to disregard the lines above, no, so let's try to cover, no, the resistances, no? So if we combine these two, then we end up with a combined value R23, no. So let's say we look at that one, no, after removing the individual resistances at the top and bottom. Now the two previous resistances, which are both 50 ohms and 120 ohms, no, will be combined in such a way that you can now call it as R, no, R23, no. So we will now give this a new name. So we call this as R, no, 23. But the question is, how much is the value of R23 if it is the combined value of 50 and 120 ohms? So we will apply the parallel principle there. Now again, now being a circuit that is in parallel, no, ang 50 and 120, then we will need to use the reciprocal principle, no, of the parallel connection to be able to get, no, the combined value of the resistance, no. So on the right side, no, so this R23 value, so we will have here the reciprocal values of 1/50, no. So the first value I think is 50, and then the other value is 120. So that's plus 1, no, over 120, no. So we will get the value. So the value for 1/R23, no, is equals to 17/600, no. So this is the sum of the two resistances there, no, of 50 and 120 in parallel. And then now we are ready to find, no, the value of R23, which will be, no, 600 divided by 17, no. So how much is that value? Okay, calculating 600/17, which is the reciprocal of the value above, gives us 35.29 ohms, no. Now again, now why are we looking for the value of R23? Because perhaps, no, after combining the previous two, no, resistances there, we are now able to connect, no, or end up with R23. Now, if we will see R23 and R1, no, you'll notice that they are now, no, they are now connected in series, no. So after combining R23, it's going to be obvious that they are now, no, in series, no, with one another, no. So actually, no, if we have a combination circuit, we could not immediately, no, find that or combine, no, the values together, no. So now, no, this one allows us to use, no, since we now simplify the expression, we now have here a series connection. So therefore, our R total, no, So if you will solve for R total in this case, so that will be R1 plus the combined value of R23, which is 35.29. So R1 is 80 ohms, whereas your R23 is 35.29. And we will have here a total value of 115.29 ohms. So that's now our value for our total resistance. Okay, having calculated RT now, again, let's say in this problem, what you will be looking for are the following. So first of all, let's say we find the total current. So how much is the total current? How much is the total resistance? And of course, we already calculated this. How much is our voltage V1? Okay, so maybe now those are some of the things that we are able to calculate. Now, so let's say now we calculate this one. So calculating for the first required value, since we solved already the total resistance. So let's say we go for determining total current, I sub t. So we will divide the total voltage, which is 18 volts, by the total resistance, which is 115.29. So substituting, this is 12 or 18 volts divided by 115.29. So that's in ohms. So therefore, now we will have a small value here. And that is, okay, so we have here 0.16. So that is if we round it off to 2 decimal places. So we have 0.16 amperes now, which is now our current. And then therefore, if we'll try to find our V1, so this is not in parallel. So the voltages here will not be the same, of course. However, we see that the current from the battery, which is I total, will be the same current that passes R23 and R1. So the current or the voltage V1, if we'll solve for V1, that must be I1 times R sub 1. But what is I sub 1? It is just equals to the total current 0.16. Because again, they are in series. And if we multiply that with 80 ohms, 80 ohm, which is the value of R1, then we have here the value of V sub 1 in volts. So we ended up with 12.8 volts for our V sub 1. So of course, if we want to find V23, which is the voltage across resistance 2 and resistance 3, since we have their total value and they are in parallel, so the two values here will share the same voltage as V23. And V23 is actually I total times R23, which is na-solve na ang R23. Kung multiplyan ta na sang 0.16, we can get the voltage here and we can get the voltage of each of the resistances. Ato ang 120 ohms, ato ang 50 ohms. So we will get their voltages, and once we get their voltages, we can get their currents as well. So it's not really difficult to find the current and the voltages of each of these resistances. And again, what rule are we simply to use when we go to the individual resistances? We can use the Ohm's law principle for that matter. But anyway, these are the three things that we are trying to find for this circuit. Now, let's say we will find the power. So another value that we will get. How much is the power in the circuit? Now, if you're trying to find the power in the whole circuit, then maybe we can use the product, no, which is V times I, no? Okay, or that's V total times, no, I total, no? Because we are looking for the power of the whole circuit. So the total voltage is 18, no? 18 volts. And if you multiply that with total current of 0.16, no, ampere, no, then this could be expressed now in watts, no. So we could have a value there in watts. So we end up with an answer of 2.88 watts, no. So the significance about knowing, no, the power rating of the circuit is that now if we convert this to kilowatt and multiply it to the number of hours, we are able to find now how much energy is being consumed by the circuit now as you use this now every hour. No? So it will eventually now give you a number of kilowatt hour now for every hour of use now for this circuit. No? But again, to get the kilowatt hour, then you will need to go now to the principle of energy, which is power, and we multiply it with time. No? So power times time is our expression for our energy. No? But maybe we are not being asked about that portion. No? So right now, this is how we find the total resistance, maybe the total current, and some other smaller components, voltage or current, for our given combination circuit. So this is already a combination of the series and parallel combination. So we could not go directly to find the circuit, because we have to identify first which portions are connected in series and which portions are connected in parallel. So if you see a parallel connection, I think that's the best part where you begin your analysis. So any portions that are connected in parallel should be combined first before you can go to any series connection. So maybe that's the rule of thumb. Now in last time, we have here our summary of our electrical power. And this is the power in a particular resistance. You've given the voltage, you can square it and then divide it by the resistance value of the resistor. Or else, if the current is provided, then you square the current and you multiply it with the value of the specific resistance. And this is a formula to get the power in a given resistance or resistor. But the power that is being provided to the entire battery, especially if I here and B is speaking of the total current and the total voltage, then maybe you can use this to determine the power of the whole circuit. Now, usually the goal of understanding power here is when we attach it to time, and power times time gives you electrical energy. So energy is power times time relationship. Now again, 1 kilowatt hour, you can write that as 1 kW HR, HR, or 1 watt of power is also volt ampere if you use V, V times I expression. Now let us say that we have this given set of equipments, and from here we will determine the energy consumed by each of these appliances. And again, there's some of them, there's only one appliance, but in the other components or other loads, there are 3, 4, maybe 2. Maybe you need more bulbs in your house, because you have to light up your house, so therefore you may need more than maybe depending on how much room do you have in your house and how much lighting do you want to have, how bright is your house. So maybe in this household they need 10, and the power rating is 20 watts for every bulb or lamp. The refrigerator is using around 400 watts. The flat iron is 1,000 watts, the power that it is needing, that it needs. And then the electric fan, each electric fan that they have there, So they have three. Maybe they have three separate rooms. So 300 watts each. And however, an air conditioning unit or AC, no, air conditioning unit is 1.5 horsepower. No? So this one is rather different. No? The way we express the power rating here is different, and it is now in horsepower. But we remember that 1 HP is 746 watts. No? And then they have two air cons in their house. No? So if this is the daily use of energy, no, or the daily use in number of hours, no, for all of these equipments, no, correspondingly, then we need to multiply the rated power with the quantity, no, and the number of hours, no, to be able to calculate the consumed, no, energy, no, energy consumption. No? So we are going to express all watt value to kilowatt, including HP, no, and then once we translate all this, then we will multiply the number of kilowatt to the quantity, no. So remember, no, if there are two of them, then this one will be multiplied twice, no, times its conversion value of 746. Now, if you change it to kilowatt, then you have to divide it by 1,000. No? Now again, multiplying these columns here will now give us our energy, no, consumption. Okay, here are some, no, reminders on how to convert. No, so all our unit of power will be changed into a kilowatt. No, so 1 horsepower will have an equivalent number of kilowatt equals to 0.746 if you divide 746 by 1,000. No? So that's how we change. So if we have 1,000 watts of power, no, for our flat iron, then dividing it by 1,000 also will now leave us, no, exactly 1 kilowatt power. No, so if it's less than 1,000, no, then you could end up with a decimal number. No, so that's how we change, no, the value from watts into kilowatt by dividing it by 1,000. No? Now the cost per kilowatt hour. So we have to assume, no, a certain value, maybe 9 pesos for every kilowatt hour, or 11. No? And then maybe now we need this column now. No? But let's check some of the values here if they are correct. No? So how did we come up with this answer, 13.43? Again, no, we multiply 2 times 1.5 times 746 times 6 hours divided by 1,000. No? So that will change the value from watt hours into kilowatt hour. No? So you have to multiply all of them times the conversion of 746 divided by 1,000. No? But let's check our value if they're right. No? Okay, so again, the products of each of these columns. No? So remember, 1.5 must be multiplied by 746 because 746 watts is 1 horsepower. So you change horsepower to watts first, times 2 air cons, times 6, and divide the whole thing, not by 1,000 to make it kilowatt hour. No? So this is now in kilowatt hour, and all of them are correct. No? And then therefore, no, all that we need is to multiply them by their, no, costs per kilowatt hour. No? So again, no, the total value here will be, no, 31.68. Now you will notice that a refrigerator is marked 24 hours exactly. No? Because you notice your refrigerator is never turned off unless there's a brownout. That's the only time that it is turned off. But basically, refrigerators are base loads. No, it's running the whole day, the whole night. No, 24 hours, 7 days a week. No, whole year. No, unless it's damaged. No, so this is basically called as a base load because it is continuously running. No, so that's why, you know, we secure the wirings in our ref, because once you use the refrigerator, it is continuously being used. No, and again, now this is now the total energy used, no, in just a matter of a day. No, so one day, this is now how we use things. No, now maybe, no, this is not exactly true in real life because there are there's energy saving devices no inside your aircon, because your aircon switches itself off no once it is very cold already no. So it may not really run or use no 13.43 kilowatt hour no in a day no, because again no there's a power saving device there that switches that on and off no, just like the refrigerator as well no. So if the refrigerator is very efficient, it's new, then maybe it will use less than this no. Okay, so again this is on an idea that the device is running continuously without switching itself off no. But there are thermostat controls no in the aircon and in the refrigerator no. Again the cost here no, we will check the costs. Okay, so what we assume is that the cost per kilowatt hour is 13 pesos. And again, the way we calculate energy is the number of equipments or quantity times the rated power, no? Like 1,000 watts. And then multiply it with the number of hours of use. No? But of course, we have to convert already the power rating to kilowatt no? By dividing your answer by 1,000. So just like the first value, you have your 13.43 no? Kilowatt hour. So if you multiply that by 13 pesos, so this must be the first value. No? So let's go back to the previous slide. No? So we get this column again, no? 174 by multiplying this kilowatt hour no? Of use or energy consumed no? By the cost per kilowatt hour of 13 pesos. So times 13 will now give you this column. No? So just like this one. So it will have a total of 411.84 pesos. No? And this is just in a day. No? So again, if this is how your equipments function, and if you multiply this times 30 days, no, then more or less, no, you will have something like what? 12,000, no? Not less than 12,000 that you will pay in a whole month. No? But again, now remember, our equipments are no designed to save energy. So maybe now you will have lesser amount to pay no at the end of the month. But this is just a rough estimate no how we calculate no our energy consumption. Now you can try this next example no, because I think no the previous ones we've already solved this no. So for the next slide, so we are given a series connected devices. So if you want to get the total resistance or total equivalent resistance, then you can simply add all of them. No? Now, one thing we notice with series connection is that when you add the resistances together, they sum up to a large number. No? So if the resistance keeps on increasing and increasing, then naturally, what happens to the current is that the current will get lower and lower now if you add more resistances in series. Now, however, if you will try to connect all of them in parallel, then maybe you will not get 18 ohms as a total, but the total will probably be much more lower. It could be lower or smaller than any of the numbers here. That could be a possibility. So what we distinctly notice with parallel connection is that the current there keeps on increasing if you combine the resistances in parallel. But if you combine or connect them in series, the current now becomes smaller and smaller instead. So those are things that we can probably notice in our circuit. So here, if the total resistance is 18 ohms, the current becomes 0.33 amperes. Now just imagine if the denominator becomes small and still the voltage is 6. So naturally, you will expect that if the total resistance is smaller than 18, then this one will naturally go up, which is in the case of parallel connected resistances. Now, for your additional activity, you can probably consider this one. And maybe if you try to analyze this, you could never connect them directly, or say that they are in series or in parallel. So you will eventually think of it in such a way that you will think of these values that are outside. How will you consider these two that are outside? Are they in series or are they in parallel, no? And then again, no, by doing that, maybe, no, you will go next, no, and in step to the next combined values, no? What values are you going to combine next, no, after you analyze these two, no? So again, no, this here, no, you are given 4 resistances, and as a practice, no, you can solve this one, no. So maybe, no, you can try that, no, as an activity. So maybe, no, you can think of the suggestion there, no, but this is more for your own, no, for your own personal, no, practice, no. So you can try this one, no. So with this, no, we end with the last slide, and I do hope, no, that you learned something for this day, no.